Okay, I think we'll start now. So the first step in moving towards the covariant formulation is the following. Okay, so what you do is usually we write some vector A, right? So that is usually written as A1 into x cap, right? Plus A2 into y cap plus A3 into z cap. For the usual three-dimensional vector, we use 1, 2, 3 for convenience, okay, so that we can write down in the index notation. That is the reason. And then because of this definition, what happens is you have the standard definition for A dot A, which comes like A1 square plus A2 square plus A3 square. Isn't it? So this is the standard definition that you have. In case if you have two different vectors, then we will have a different expression. A dot B can be written as A1 B1 plus A2 B2 plus A3 B3. So like this, you will be having the expression for the A dot B. Now the point that the notation for the covariant vector and the contravariant vector is that there are two suffixes are there, isn't it? There's 1, 1, 2, 2, etc. So one of the suffix we are going to keep it in the lower place, and the other one we are going to put it in the upstairs. So that means we are going to rewrite, simply we are going to rewrite like this, but then we will redefine like this. So A1, one of them will be in the lower index. The B1 we can write it in the upper index by having another definition. So we will see what then plus we can write down like this A2 B2. These are all not powers, but this is only we say it is lower index and upper index. Then we have an A3 into B3. Then this A dot B is now written as not in the vector, that is the arrow will not be there, but now you use the index notation. You say that AI, then BI, this I will be in the superscript notation. So if you do like this, okay, one particular index in the lower place and another index in the upper place, if you are going to do that, we say that this is the covariant contravariant notation. Okay, so the one which is there here, right, the one which is the lower one, that is known as the covariant form. This is known as the covariant vector, the one which is in the lower index. And the one that is written in the upper index, this particular one. So this is what is known as the contravariant vector. So by that, what is the meaning? See, is that it comes from the definition. So now for the case of the Euclidean geometry, there is no distinction between these two. So that is the interesting point. Because this is three-dimensional Euclidean vector, and for the case of the Euclidean three-dimensional case, there is no difference at all between the covariant and contravariant. So that means these two are identically same, and therefore what happens is our definition is looking identical, which means that the lower version, that is the covariant version, is nothing but A1, A2, A3. Now what is this A1, A2, A3 is? It is the same A1, A2, A3 that is there here. So it's there here, right? This one. So I'm talking about this one. So when you remove the unit vectors, okay, unit vectors you delete. What is left out is the components A1, A2, A3. That A1, A2, A3 is what is written down as the components, and we give the suffix I, where I takes the value 1, 2, and 3. So this is the way you define. And now for the contravariant case, what happens is you are going to make an identical definition. That means the contravariant vector A superscript I is once again the same thing, which is A1, A2, A3. So these two are identically same. When this is the situation, when you take the dot product, okay, this is the self dot product I'm talking about, this one A dot A. Okay, so this A dot A, now we can write down. How do you write down is this AI here and then here AI, and which is equal to A1 plus A2 plus A3. And because numerically speaking their values are equal, because of this reason A1 into A1 there is no need to write like this, we can write A1 square. So that is what is the expression that we have here. So what is our idea, or what is the conclusion is that in the case of the three-dimensional Euclidean case, the subscript vector and the superscript vector, they are identically same, and therefore there is no difference or distinction between the contravariant form and the covariant form. Now this is the point to be noted, first point. Second point to be noted is that in the dot product that you're going to have, whether it is A dot A or it is A dot B, whatever be the dot product that you have, the point that you have to notice there is a plus here. So all of them are positive values, plus here, and the first value here is also plus is there. Okay, numerical values maybe that it can take any numerical value. For example, A2 can be negative, B2 can be negative. Those things are fine, but the definition gives you a plus here. Is there anyone joining still? I don't know. Yeah, you are. Okay, so 35, 35 are joined. Okay, that's fine. So now this is the situation that you have the positive in all the three places. This is the place where you have to give the no. That is why we are giving importance to the dot product. Now, what is the point to be noted is that when you have a quantity plus y square plus z square, this is the usual expression for the radius, right? R square, or we say that the distance from the origin to the point x, y, z. This is how you write. Now, this expression x square plus y square plus z square is looking like a dot product, isn't it? So that means this is the first component, this is second component, and this is third component. So we don't want to use. Okay. So instead of saying x, y, z, we will rename like this. So this is x1 square plus x2 square plus x3 square. That will be equal to r square. So this r square is what is the usual formula for x square plus y square plus z square. But the point is that we don't want to have x, y, z, etc. Because after z, we don't know what will come. We don't have another variable. But if you write with the notation 1, 2, 3, etc., when you are going to fourth dimension, I can put x4. Fifth dimension, I can put x5. So that is an advantage of this. So once you bring to this 1, 2, 3 notation, now this is clear that x1 square is nothing but x1 into x1. x2 square is nothing but x2 into x2. And similarly, x3 into x3. Because in the Cartesian usual 3D case, the lower and the upper indices have no difference. We can once again rewrite this and we say that this is r square. And this expression is nothing but we can write down that xi, then again we write xi. So this is the notation that you have, which is equal to r square. So this is what is known as the index notation. And now the usual dot product, these are the usual dot product, as you can see that in the dot product notation, and the dot product notation gives you a positive value for all the symbols here. So this is also a plus here. So now the question is that when you are moving to the case of relativity, that means when you are going to make the Lorentz transformation, you learned something in the last semester. What did you learn is that at the end of the last semester, the quantity that is Lorentz invariant is the following. So I will write down which quantity is Lorentz invariant. Is the quantity given by Ct whole square. Why the product comes with the Ct? You already know that the dimension, if you see, this is meter per second and this is second. So this product will have the same dimension as the distance. So that is, this connection has to come here. Here you see x square, x means meter, right? Y is also meter. So now c into t will have the same dimension. That is why Ct comes. Okay, time alone will not come. Because if there is only time is there, then we can't make the addition. If you want to add, all of them should have the same dimension. Okay, then only you can subtract or add. So this minus, there is a minus here now, minus r square. Now this r square is this one which we are talking about. So this particular expression for the r square is the same r square now entering into the Lorentz invariance calculation. Now this quantity is 0. This is a scalar, right? Because this is a scalar now, this quantity will remain the same. That means invariant. for different, for invariant for whom means for all the people who are in the respective frames of reference. That means a person is sitting in one frame of reference, another person is sitting in another frame of reference, and these frames of reference are moving with uniform velocity. You know that they are inertial frames. So for whoever be the, that is for independent of the person, whoever is the person sitting in any of the reference frame, that particular person will measure 0 for the quantity c square t square minus r square. So that is why it is called invariant. But suppose, but in the contrary to this, now suppose if you measure only r square, suppose if you measure only r square, then what will happen is, if you do like this measurement, one person will measure r prime square, the another person will measure r square. Let us say that this is the you know the usual notation, right? The person sitting with the frame of reference capital O, and another person sitting in a frame of reference which is moving O prime. Okay, then only primes are coming into picture. So one fellow will measure r square, another fellow will measure r prime square, and they are not equal. So therefore, the quantity r square is not at all Lorentz invariant. So when two people measure two different things, it is difficult to correlate, or it is difficult to interpret the results. That is why people are interested to find out which quantities are Lorentz invariant. Now, once you have a scalar like 0, that scalar will not change from frame to frame. So therefore, this if you measure c square t square minus r square, then the person in the primed coordinate system will measure c square t prime square minus r prime square. That will be equal to 0. And what about this person? This person will measure c square t square minus r square. And if you simplify, that also will go to 0. So therefore, whether it is primed frame of reference or unprimed frame of reference, both the people will measure 0, and therefore this quantity is known as Lorentz invariant. So this is something which you already know from classical mechanics. Now the point to be noted is the following. What is the point to be noted is, this has three components. Remember that this r is a vector quantity. Therefore r square is here, it is there. R square means it is the sum of the three quantities. Okay, this is not a single term. So therefore what happens is, this is a minus, you have an x square minus y square minus z square equal to 0. This one. Then the first quantity is ct whole square. So you have a ct whole square is there. So it is clear that we will be having a quantity like this, and that is going to 0. So that is fine. But there is what is the trouble now coming to picture is that this expression has a plus here, that is okay, but there are minuses are there. So you have 3 minus signs are there here. Here one, here one, here one. But your dot product will generate only positive. So now you ask the question, okay, what is the question that you are asking is, if you want to consider a 4-dimensional Euclidean space, consider 4-dimensional Euclidean space, which means that you are going to have 4 axes in the 4-dimensional case. Then what will happen to this kind of a product is that I will be having xi, xi. So one in the superscript, one in the subscript will give me x1, x1 plus x2, x2 plus x3, x3 plus x4, x4. And that's all about it. And you can always say like this x1 into x1, the first term that you have written, is actually something square, that is x1 square, which is equivalent to this quantity. So we can always identify that, okay, the first term corresponding to c into t, the second term will corresponding to x, the third one corresponding to y, the fourth term corresponding to z. It looks very fine. Everything looks fine. And this is what we say that the 4-dimensional dot product. Okay, these are all looking fine only, but there is a trouble coming into picture is that these things are now plus here. We can't use this dot product for our problem now because of the minus coming into picture. So therefore, because of this reason, we cannot use the standard 4-dimensional Euclidean space dot product. That is where the trouble comes into picture. And then you'll have to think. So the question is that the idea is like this: you do something. Ultimately, you have to bring the minus sign here. Okay. So remember, where do you want to bring the minus sign? Here you have to bring a minus, and here you have to bring minus, and here. Do something and bring. So that something is what we are going to do, some kind of a tricky thing, and that's what we are going to see. What we are going to see, let us see. Let me therefore write down like this. First element is C into T. Second element is X. The next element is Y, next element is Z. So the identification of the element is clear, right? You see, this one is the first element. So first element is x1 square. Here it is ct whole square. Therefore, ct is the first element I have written. So second element is the square of what? Square of x. Therefore, that x I am writing here. So like this, all the four elements are identified. So that is okay. Okay, that's all. Okay, no more identity. Fine. Elements are identified. Now the point is that somehow we have to generate negative values for the xyz, whereas positive value for the ct should be maintained. Okay, what are you going to do? That is a question. The interesting thing is this: you have to do something and then bring. That something is that let us multiply by 1 here. If I multiply by 1, ct into 1 is how much? Ct into 1 will give you ct. Therefore, I have the positive value. This is clear, right? Then what should be your second value? I want a negative value for the second element. I want a negative value for the third and fourth. Therefore, what you do is you put a minus 1 here. If you put a minus 1, what happens is now you have to make this product. And remember that this matrix multiplication requires you have to take this and then you have to take the column and then multiply and then add everything. Then only you get a CT. Then what will happen is if you put a 1 here, then trouble will come because x has to be added here. So you put a 0. So that ct into 1 plus x into 0 plus y into 0 plus z into 0. So that gives you ct. So that's how it comes here. And similarly, what happens to the second one? Let us see. Ct into 0. I don't want ct now. So ct into 0 plus x into minus 1. So x into minus 1 will give you minus x. Then y into 0 plus z into 0. If you do like this, now I am able to successfully generate a minus sign. Somehow I got a minus sign, right? That's what you have to do. Something you have to do and generate a minus sign for the xyz component. And if this idea is clear, for the case of the y, where will you put a minus 1? For the ct part, 0 should be there. For the x component also 0 should be there. For the y component, I want a minus 1. For the z component, again 0 should be there. Then only I'll get a minus y. You can now take a product, right? This one into this one. Then only it will come. And similarly, for the case of the last element, where should be the minus 1? The minus 1 should be only at the last. In that case, I will be getting a minus z here. Now what happened? You see, this is how you are starting. So this is the one that you start. I started with the all positive values. This is my final one. So finally, my ending point is that I am able to generate negative values for the xyz. So how did you make this achievement? This achievement has come through because of something here, okay, which is we don't require a proper physical meaning for this. But however, this kind of a matrix is going to help you to make this kind of conversion, and we are going to call this as the metric tensor. And remember that this is not the Euclidean space, right? This is not Euclidean space. This I already told you in the classical mechanics, where Euclidean space means all of them should be space component. Time component should not be there. So as you already know that time component is entering into picture in our relativity. Therefore, this is not the Euclidean space, but rather it is known as the Minkowski space. So therefore, I will say that this is what is known as the metric tensor for the Minkowski space. So this tensor is going to help you to do the conversion. Now that these things are looking lengthy and it occupies a lot of space, people want to discover some kind of compact notation. And this compact notation is what is known as index notation. So now what you do is, since you started away like this entire thing is what is represented by a shorthand notation x mu. So whether you are going to start with a lower index or upper index, it doesn't matter. But people have started like this. Okay, so we are also following the same tradition, and therefore the one that you started with is known as the, somebody is joining. Ashwin. Okay. Okay, so whatever you started with, that is usually known as the contravariant version. Contravariant means it is one way of one style of writing. Okay, it is there is no difference between one version and other version. We have to manipulate with the two versions together with this metric tensor to generate whatever we want. Now, whatever we want means what is that we want to generate? Remember once again, what is that we want to generate is this is the one we want to generate. We are interested in this. So the question is, how will you generate this quantity? Now we got the answer. We will be successfully able to generate this quantity if we have a metric tensor given by the 4x4 matrix like this. So this metric tensor is also, of course, tensors are just matrices only. Therefore, you are going to use a 4x4 matrix for this. And we are going to give the name for this once again because we need a shorthand notation. We don't want to write a lot of space consuming object like this. So we are going to give a name like this. This is what is known as G mu nu. So I'll write down like this, G mu nu. That is how you write like this. So one of them will be like this and another one will be lower one. Now why do you want to write this lower upper combination is according to the Einstein convention, one lower and one upper, that combination should come so that you can make use of the product rule. Okay, that is the reason why do you want to use upper lower conversion. If both of them are upper, we should not do the product. So that is the convention or the rule given by the Einstein. And now that you are making a product, how do you know that we are making a product? It is there, right? Ct into 1, then x into 0. So this kind of product and addition is going on, right? That is what is known as the Einstein summation convention. Summation means where is summation? Ct into 1, then you have a plus, that plus only is summation. Then x into 0, then plus y into 0. So we have to perform the Einstein summation if one index is upper and one index is lower. So because we are already performing the summation, you fix one of them is upper and therefore you have to fix another one lower. Okay, that is the reason why lower is coming into picture. Okay, so now if this is the situation, how will you write the entire big equation is like this. The entire big equation looks like this, x mu, then we have a G mu nu. So that is the only this much space now it occupies. It looks compact. So that will be equal to, so that is equal to this object. Now as you can see that this mu and this mu will be what is known as the index for the summation, and therefore once you perform the summation according to the Einstein convention, that particular index will disappear. That is the general rule. The index itself will disappear. You can, of course, you can see here. How will it disappear means it is all, it's all clear here. You see here. When you have written down x1 square plus x2 square plus x3 square, x1 square is nothing but x1 into x1. Like that you write. So that is compactly written as xi, where I runs from 1, 2, 3. So once you write like this, this is actually the summation of xi square. So this I itself will disappear. You don't require them after finishing the summation. Okay, you don't require any more. That's the meaning. Only thing is we want how many i's are there? I equal to 1, 2, 3. After that, full stop. So this information only is required. Whether 4 is there, 5 is there. That will decide how many terms are there in the summation. But the index value I itself is not at all required. Okay, so that means in the boxed expression, here you have a box expression, you don't have the value for I. So here you see that in this equation, I value is not at all required. So that is why we say that when we perform the Einstein summation, the index will completely disappear, and therefore this particular index is known as dummy index. Okay, so once that is clear, okay, so we are here now. So therefore this mu will disappear. So if mu disappears, what is left out? only one nu is left out. That nu should be transferred to the right hand side. So therefore, that vector will be x. So originally I started with this vector x here. So I can use capital X. Of course, it will be sometimes it is better to use capital X also, but it doesn't matter. So once mu is gone, what is left out is we are left out with nu. So that's all. So this is the equation in the compact notation corresponding to this big expression. Okay, this into this equal to this. Okay, so that is written in the compact notation like this. Our conclusion, what is the conclusion is that if you start with the contravariant, this is a contravariant, right? If you start with the contravariant vector, I will be able to generate a covariant vector if I multiply by the metric tensor given by this. And this is once again can be written in another compact style. What way to write is, interestingly, this is a diagonal matrix. You see this? This matrix is a diagonal matrix. Diagonal matrix means the elements in the diagonal only will be present which are non-zero. It has to be non-zero. At least some of them. Okay, that is very important. If all of them are zero, then it is not a diagonal matrix. That is one condition. Second condition is off diagonal elements must be zero. So off diagonal means anything other than diagonal element must be compulsorily zero. Only then it is called a diagonal. So we can write down that this is the diagonal matrix containing the diagonal elements 1, minus 1, minus 1, minus 1. So this is another way of writing down this particular matrix. Okay, so now you understand that these are the two ways of writing down the expression, and this is what we are going to give the name G mu nu. So now you understood that the purpose of this particular diagonal matrix is to convert a covariant vector to the contravariant vector. Okay, that is the idea. So now the advantage of this is that I am able to generate the minus sign. So now using this notation, what happens is that if you want to start x mu as the definition, what is your definition? C into t first element, x second element, y z. This is where x mu. X mu means usually sometimes in the textbooks they write in a capital letter, but it is not very important to use capital etc. So whether you use capital X or a small x is fine. Okay. The meaning of this, what is the meaning of this is? The meaning is this is the, maybe I'll write here for comfortable. This is what is known as the first element, x mu, right? Now mu will take the value 0, 1, 2, 3. This 1, 2, 3 is the same 1, 2, 3 in the Euclidean. And because of the time component, we say that there is one more element, fourth element. Okay, instead of going to 4, because of the traditional way of writing the summation from 0, they started with the 0th component. Anyway, it doesn't matter whether you write 1, 2, 3, 4 or 0, 1, 2, 3. Both are same, but you have some tradition, right? The tradition is like this, and as always you write n equal to 0 to infinity. So there is a tradition of writing the summation starting from 0 most of the time. So because of this reason, let us have a 0 here. That is the idea. So that this is the 0th component. Then this will be the first component. This will be the second component. That will be the third component. So that is the meaning of this. So if you want to define this object as the contravariant vector, then okay, if you then what happens is what will be the corresponding covariant vector? Just now you have calculated. So the covariant vector will be the one with the lower index. That will be given by first element is positive, second element, third element, and the last element will be negative. So that is a calculation that we have done. Here it is. This matrix now after here you got minus n, right? So that is the meaning of that. So if you start with the contravariant, the ending object, this particular ending object will be the x, the what is known as the this one. If you call it as a superscript, then we say that this is subscript. But initially you can start with anything if you do not know what variables to start. Okay, mu, k, whatever you want you can put it. But why I am not using a mu here is very careful. Here you see that there is a new here. It doesn't matter whether you put a new here or mu here, but the trouble is that since already mu is used here, you cannot use one more here. You can't say G mu mu. So that is the reason mu is already occupied. That is why we are using another symbol. Okay, so it doesn't matter which one you are going to use, depending on the requirement, you can always choose. But for the time being, only for definition purposes, we don't have to change this to new. Okay, so what I'm trying to say is, it doesn't matter whether you put a new here or whether you put a mu here. The point to be noted is, it is the one with the lower index. This is the one in the upper index. Okay, so only if requirement is there, we will change mu to new. Okay, if there is no requirement or there is no demanding condition, we can use the same mu here. That is the meaning. So we are now able to have this kind of minuses here. So what is an advantage of this? Advantage is, because of this reason, our conclusion is, how will you write this quantity x mu x mu? That is what I am trying to say. It doesn't matter which way you write. Either you can write x mu. You can write like this. If you write like this, you know what it is. Two mu's are there here. One appearing in the upper index. Once again appearing in the lower index. Therefore, it has to be an Einstein summation. That means summation will be done by the product. So that means there is a product is already there, right? There's a multiplication. This dot is not required, but I'm showing. So multiplication is already there. Summation has to be done for each component. That means CT into CT. CT into CT is CT whole square. Then plus, that is the Einstein summation. This is the Einstein summation plus this element into that element. So first element is x, second element is minus x, plus first element is y, second element is minus y. So Sunish. Okay. Then plus third element into third element. So this is the zeroth element, first element, second element, third element. And if you simplify, you are able to see that three minuses are now coming into picture. Okay, this is what we want. This is the invariant quantity, right? So finally, our idea is that using the idea of the contravariant vector, covariant vector, and the concept of the metric tensor, we are able to generate this quantity, which is an invariant under Lorentz transformation. So once this idea is clear, we can extend the same idea and concept to rewrite many of the equations in electrodynamics. That's all about it. Okay, so this is the basic concept that we are going to use. So this is one concept. Okay, this is over. Okay, wait, it's not coming. The second thing is, once this is clear, similarly, you can define some additional things. What additional thing is, similar to the dot product, we can also talk about the divergence. Okay, suppose if you want to talk about the divergence of some quantity, how will you write? This is usually written as dou by dou x, then you have a dou by dou y, then you have a dou by dou z. So that operator is operating on this f is a vector, so I can write down that this is going to operate on the f vector. So of course, if you simplify, you know what it is. Dou by dou x of the x component of fx plus dou by dou y of the y component of f vector. Like that, you can simplify. This is the usual 3D. Want to know what will happen if you extend it to the Minkowski 4D case. So for that, what you do is, before directly writing down, so our understanding is like this. What is our understanding is, there is a x here, there is a y here, there is a z here. So therefore, this set of elements are x, y, z is a set that you have. So if you have the set of elements x, y, z, it is a tradition to say that is how you start with. So the starting one will be the contravariant version. So we say that this is the contravariant version. And then the corresponding covariant version will be there with the lower index. And remember, for the case of the three-dimensional Euclidean space, there is no difference at all. And of course, you can ask the question, what do you mean by this kind of identical expression without any difference? It's very simple. If you write down x, y, z like this, then you'll have, because this is three elements, the matrix will be a 3 by 3 matrix. So I have to get x, y, z here. So if it is the case, what will you fill? You have to fill here. You do something. No, that is what you have done. You do something here so that I will generate the another version of the vector. One version is contravariant, other version is covariant. So what will you fill here means you have to fill like this. So 1 times x will be here, and 1 times y will be this, and 1 times z will be this. And I don't want to have other types of combinations, therefore put a 0 there. And now you see that this multiplied by that will give you this. Now this is actually the metric tensor for the usual 3-dimensional Euclidean space. So that is why, of course, this is being an identity matrix. You don't feel that you are doing a multiplication. Actually, you are multiplying and getting, but you don't even feel that we are performing this kind of a multiplication. So that is why we say that there is no difference between this one is a contravariant here and this is covariant. Okay, so that is the reason. Now, if this idea is clear for the case of the 3-dimensional Euclidean, you ask the question, what will happen to the 4-dimensional Minkowski? So that is how you ask the question, and then you can write down like this. So to start with, for the case of the 4D, what will happen? We'll see. The 4D case, you already know what it is. So this is given by CT. Then you have a X. Then you have a Y. Then you have a Z. And here, yeah, I want to tell something about the derivative. Here, yeah, this is fine. So you have a X here, you have Y here, you have Z here. So because of that reason, what happens is we can write down this quantity as, we can compactly written this quantity as dou divided by, you see this dou divided by, then dou, then this x comma y comma z, all the three combined is x mu. Therefore, put x mu here. That is how you have to put. Okay, so this is the notation for the divergence. So we say that this is the contravariant derivative. We say that contravariant derivative. It is of course these derivatives are naturally taken place because of the dou by dou x, etc. And in particular for our case, we can say that this is known as the 4-dimensional divergence, because this is the divergence, right? And therefore we can say that this particular object is known as 4-dimensional divergence. And this will operate on this particular f operator. Of course, that will f has to be written down here. So how do you write f is that you write f here. Okay, but the question is that where will you put the subscript or superscript? And since you are going to start with the original f, this has to be put here. Mu will be in the superscript. This is how you'll be writing. And wait, I don't have the space for deleting. 1 second, I'll delete this. I need some space so that I can explain here. Okay, so there is important point now. So all these things are clear. How you have written, all these things are clear. But now we don't want to write so many. We are always looking for compact notation, right? So people feel that even this is not compact. Okay, we can still reduce and write it in as compact as possible in such a way that the summation is implied. So you have to remember one thing, summation is there. Where is summation? You see that this divergence is what? The divergence is actually dou f by dou x plus dou f by dou y. So the information of the summation is not there if you write in the comma version. And if you write in this version also dou f mu by dou x mu, the information about the summation is not clear. You get a doubt whether to sum or you don't have to sum. You don't know that. So therefore, the summation information should also be visible. It will be visible is one index should be lower and one index should be upper. Therefore, what happens is this dou by dou x mu, you write it like this in a compact way, dou mu. Which one I am writing? Are you able to see this? So this particular portion. Only that much. So the one which I am showing in the green color, only that you represent it by this. You can ask the question, why do you want to represent? The reason is After finishing this, what are you going to write? I am going to write f mu. You see that I'm going to write f mu. Now, when you write this, when I am writing f mu, mu appears in the upstairs or in the upper index. Since it is already appearing in the upper index, this has to be in the lower index. Only then summation will be possible. Otherwise, you can't have summation rule. So therefore, plus dou f by dou z is there. So this kind of summation will be automatically taken care if you have one lower index and one upper index. And therefore, we say that this is the actual four-dimensional divergence. So this is the notation. And what is the meaning of this dou mu? Dou mu, and remember that once again I'll write if you want, where dou mu is nothing but dou divided by dou of the x mu. So this definition should be clear to you without any confusion. And based on this definition, you write like this, where the traditional f mu is the starting, whatever vector is given to you, that is the, if it is three-dimensional, three elements will be there, four-dimensional, four components will be there, etc. So those things are clear. Now comes the point. Three parts are okay. When you are extending to this, three parts are okay. Okay. Suppose if I say that mu takes the value 0, 1, 2, 3, 1, 2, 3 part is clear because this is 1, this is 2, this is 3. Now the question is about the zeroth part. So what will be the respective element for the zeroth part? So that is what you have to write down. Once you write that, then the four-dimensional divergence will be clear. And that is once again easy. So what is the zeroth part? Zeroth part is CT. And therefore I can now write down, now I will write down. So this is your dou mu. So that will be equal to dou divided by dou x mu. So what is that? It is nothing but the set of four elements that we are going to write down. It is dou divided by dou of the first element, comma, dou divided by dou of the second element, then comma. Similarly, you fill it out for the next elements. That's all. That set will be the object. And because C is a constant, there is no point in keeping it inside the derivative. Therefore, I can write down 1 by C into dou by dou t. Then comma, dou by dou x, comma, dou by dou y, comma, dou by dou z. So if you have this kind of an object, this is what is known as dou mu. This is very important. Now, if you know this, then after that, it's only rewriting the equation, and then it's only a matter of simple kind of rearrangement. There's no difficulty. So this is one thing. And not only that, okay, this is fine. And what about the another version of the, another version means the contravariant version you can write down. So this dou mu is by definition, you have to remember this mu is a lower, right? Therefore, the opposite you have to write. So opposite means since it is lower, you write upper here. That is equal to dou divided by, here what will you do? X mu is in the upper case. Now you have to write in the lower case. Therefore, dou x mu. Whatever is there here, you write opposite. That is the meaning of that. And that is equal to, you know what to do. What is this x mu? So I'll once again just remember what we are doing. This x mu, you should remember what it is. Only then you can do the calculation now. So what is that x mu? X suffix, that is lowercase mu. So you remember what is there. Here it is there. This is the one I'm talking about. So only if you remember this, now we can do the simplification. This one. Okay. So keep these four elements and then substitute there. You will get the expression. Okay. Let us go back there and then substitute. That is equal to. So it is as usual. The partial derivative of dou divided by of dou of first element. First element is CT, comma, dou by dou of second element. Second element is minus x. Third element is minus y. And the last fourth element is also the negative. Now once that is clear, so finally we will be having a dou mu given by So let us simplify this. 1 by C dou by dou t, comma, minus of the dou by dou x, comma, minus of the dou by dou y, minus of the dou by dou z. That's all. So these are the important relations. I'll say keep 1 and 2 for example. So you have the expression for this. One is known as the covariant derivative. This is known as the contravariant derivative. So we frequently we will be using the covariant derivative for the divergence. You remember this kind of object? Dou is there, and then the mu will be there in the lower index. So that is known as the covariant derivative. This derivative will appear in the divergence. You verify whether it is appearing or not. It is there, right? So this is the expression for the divergence. So whenever we are talking about the divergence, the derivative notation will be there. Afterwards, the Greek index will come in the lower index. This is known as the covariant derivative. And in our case, of course, the Maxwell equation or whatever that you are going to do in the electrodynamics, they will be differential operators. Like because of that reason, the equations will have dou mu like this, and therefore the final conclusion is what we are going to say, that the equations of electrodynamics are written in the covariant form. They are actually covariant derivatives are there. So that is the reason why we are getting this kind of terminology. Okay, now what are the definitions that are now required? Finally, let me put a tick mark here. So what is very important is, see, I'll put a tick here. This one. So this is the starting, right? So x mu. So the definition for the x mu will be all positive. This is the first point. Second point, you should know about this particular metric tensor. And then once you are going to lower this index, okay, this is the lower index now. Once you put the lower index, you will be getting space components negative. Only space components negative. Time component is positive as it is original, as original positive. So that's all. This is the initial first thing you have to know, where derivatives are absent. There are no derivatives. Now, once this is clear, the second important point is that the conversion from the lower index to the upper index can be done using this kind of multiplication. So that is the second thing that you need to know. And after that, what is required is that you should know that the traditional dot product is extended to 4-dimensional case. It is the same idea about the dot product, but now it is extended to the 4-dimensional case with the help of lower and upper version, so that minus is generated here. Okay, that's the next important concept. And finally, two more important concepts are these two derivatives. So one is this derivative that you have, known as the covariant derivative, and the last one that you have is the contravariant derivative. This is the last one. Only this much. If you know this, you can rewrite the equations in a much compact way, and those compact ways are also the equations that are going to satisfy the invariance property. So that is why it gains some importance. Okay, so why people are interested in doing all this kind of work is that ultimately the way in which you are going to write down the equations of electrodynamics are such that they will be invariant under Lorentz transformation. That means invariant under Lorentz transformation means a person in one frame of reference and a person in another frame of reference will observe the same result, or both the people will make same conclusion. That is the meaning of Lorentz invariance. Okay, so this is the required introduction. Once it is there, let us see how to rewrite some equations. So till this, okay, do you have any? You want to ask any questions now? Hello.
Hello, sir. Hello, sir. Am I audible? Hello.
Hello. Is there anybody? Yeah, but anyone is planning to ask doubt?
Hello, sir.
Okay.
Hello, sir.
To join Ashraf, now only joining. Where is he? Okay then. So in that case, we'll make a
Hello, sir.
the next example. Now the question is this: now once these kinds of basics are available, the first thing that you can understand is that how to rewrite the energy momentum relation in classical mechanics. We have energy relation is there, right? E square equal to p square c square plus m square c to the power 4. Hey, what is that? Someone is asking. I don't know. I'm not able to hear any sound. Gokula Krishnan, yes. Some students are speaking, but can you hear me? No, I am not able to hear. That's what I don't know what happened.
Hello, sir.
Whether within students you are able to hear? Okay, then I don't. Only for me it is not there. Maybe I have to stop the sharing. I don't know. Okay, I'll stop sharing. My mic is always on only, isn't it? So
Hello, sir. Hello.
hello, hey, now can you speak? I have restarted.
Hello, sir.
Oh yes, yes. Gokula Krishnan now.
Yes, sir. Okay.
Yeah, tell what is your doubt.
Sir, dou superscript mu is called what variant, sir? Contra or covariant,
Contravariant.
sir?
Superscript means top, right? Top means upstairs. That is known as the contravariant.
Sir, but dou power, I mean, dou superscript mu is equal to dou by dou of x subscript mu. Yes, sir. Is it, sir?
Yes. Okay. That I understood. Yeah, it looks like that, right? One is up and other is down. Yeah, that is how the convention. Once again, I'll go back to the screen. I'll show the screen here. Let us hope that the sound will not be disturbed. Yeah. So you are talking about yeah, that is quite natural doubt. So this definition, this particular definition is this. Okay, this is given by dou divided by dou x mu. So this is the definition for this. Okay, na? So this is definition. So as you see that this mu is lower, whereas this is your doubt, right?
Yes, sir. Yes, sir.
So this is the definition. Why this definition has come is, as I already told you, that the divergence has to be, this particular operator has to operate on a vector, right? Some vector. So some f vector will be there. How do you write f vector? F vector has to be written like this. So this object has to operate on this object. Okay, suppose if you want to put an upper index for this, then the trouble comes. What is the trouble is f will be an upper index, but you want to define dou also with an upper index because this one is upper. Okay, so if you want to do that, both of them are upper. Now this is not summation. Okay, for the divergence, summation is required, right? First component plus second component plus third component. So for that reason, because summation rule should also be included when you are doing this kind of work, and that is the reason why this kind of thing is defined as. So we are going to define like this, known as a covariant derivative. So covariant derivative equal to partial derivative of the contravariant vector. That is how you have to understand. Okay.
Okay.
Yeah, any other question? Okay, then fine. So now we will see how to rewrite the equation, whatever equation that is there in physics. For example, to start with, let us have the energy momentum equation in classical mechanics. Now here, basic idea is the following. You have to identify a vector, otherwise you cannot rewrite. Identify a three-dimensional vector. So you have to identify a three-dimensional vector and you have to look for some kind of time component. See, is somehow, yeah. What is this sound? Ritesh Bharat, admit. So is this point clear? So whenever you want to rewrite in the covariant notation, somehow you have to search for the usual three-dimensional vector, and you should also search for a time component present in the equation, whatever equation that you start with. So now this is the energy momentum relation, I mean relativistic energy momentum relation in the classical mechanics. Now since it is already an equation that is derived for relativity, you must have some information about the time component and the usual three-dimensional component or vector. I'm talking about 3D vector. So if you look at this, energy is not a vector. Forget about it. Okay, this is C, mass C. So which one will be possible vector is that only this particular quantity should be a vector quantity. As you can see that P square means it has to be P dot P. So therefore you are able to identify the usual three-dimensional vector, first part. And the second part is which quantity will be connected with the time. That is the question. The answer is usually the one with the C, because you know that what you know from till now is the first element comes like a CT, the second, the third, and the fourth element are the usual XYZ of the 3D Euclidean. Therefore, if at all there is a time component coming into picture, that has something to do with the velocity of light. So wherever the velocity of light is coming into picture, that component should be put in the as the zeroth component, because this is how you are going to write, right, an object, and we say that this is some quantity mu like this. So therefore this is the zeroth component, if you want to say zeroth component. So that should be the one mixed with the speed of light. The other three should be the traditional three-dimensional vector. So this is how the idea is there, and in that way you have to look at this this equation and do some kind of algebraic manipulation. You can do whatever you want, but do something and then identify which one will be the time component, that means the zeroth component, and what is the quantity identified as the usual 3D case. That is the idea. So for that purpose, what you do is this C square, let us take common and then divide it. I am taking a C square from here, I am taking a C square here, and I'll divide it in the left hand side. Then what will be the expression remaining is MC whole square. Is it okay? You get M square C square. So that is this is the equation that you have. And now, as you can see that E by C is there. So let me write down E by C. That is a whole square. Then P square, I'll bring it to the left hand side. I need some space. Okay, maybe shall I erase this? You remember this, I will erase this. So you should write this is called the 4-dimensional vector. So the 4-dimensional vector will be, remember, this is a 4-dimensional vector. I didn't tell the terminology. Okay, and now I will tell. This is known as the 4 vector. Okay, 4 vector means 4 components should be there. But this is not the usual 4 component Euclidean vector. That is also you should be careful. In the case of the Euclidean also, you can have 4-dimensional Euclidean vector. That is also there. But this is not that, because there is a time component entering into picture, and therefore this 4 vector is the vector corresponding to the Minkowski space. That is a point to be noted. So now you should remember what is the plan of our rewriting this equation. Somehow we have to manipulate in such a way that one component will contain time or the speed of light, whatever it is. Speed of light will come all the time, and somehow you have to identify the usual 3D vector. So that is the plan. Let us see how to manipulate this. So for that I'll delete this. Okay, so minus this P square. So this P square is what I'm going to bring it to the left hand side. I'll say that this is X component of the momentum, Y component of the momentum, and the Z component of the momentum square. So that is why this P square is there, and therefore that must be equal to, on the right hand side I have MC whole square. So if this is clear, now you will be able to recognize. What you have to recognize is the first component is positive. You remember this. First component is positive. Second component is negative. Third component is negative. Say minus Py square minus Pz square. So therefore, it is in the case of the relativity, this always takes place like this. So now we can, if this understanding is clear, now you will be able to tell which one will be the, or how do you write the contravariant vector and how do you write the covariant vector. So the contravariant vector will be the one with all positive. That means E by C, comma, Px, comma, Py, comma, Pz. And then the correspondingly, the one with the lower index will correspond to the negative values. So where will be the negative? All the 3 space components will be negative. That means minus Px, minus Py, minus Pz, comma, comma. So you know on what basis we are making this kind of definition. We have been doing this from the beginning, that we have an equation like Ct whole square minus x square minus y square minus z square. So this is the equation that we have been discussing from the beginning, and this equation is also looking like that. Can you see that this particular equation is looking very similar to this equation? Instead of Ct, I have E by C. Instead of xyz, I have px, py, pz. So therefore, you can easily write down these 2 things, and remember that these 2 things are connected by the same metric tensor. Metric tensor will not change because of this definition. As usual, we can say that x mu multiplied by the g mu nu will be equal to x mu. Same definition, same objects will follow this particular rule, and therefore now what happened is we are able to successfully define one covector and one contravariant vector corresponding to this energy momentum relation. So once you write this, what happens finally is that, okay, so finally what happens is that, so what is this entire equation? The entire equation, that is 4 terms, first term, second term, third term, fourth term, all the terms will be now written as x mu. Okay, that's all. All the 4 terms are written down like this. That will be equal to mc whole square. And there is nothing to do. That's all over. So that means we are now in a position to write down the energy momentum relation in a much compact way. You see what is the original appearance? This is the original appearance. This is the expression that you know from the standard way of writing in the relativity. this equation appearance, and the last one that right now that we have, this is the new appearance that you got. Now we say that this new appearance is preferred, or we say that this new appearance gives you more information. What information it gives is that this right hand side quantity, this particular thing, is a scalar. Okay, you know from your basic analysis of vector and tensor, what you know is vector is a quantity whose components will transform according to the coordinate transformation. That is the definition of vector. So vector is what means if you have a1 into x cap plus a2 into y cap plus a3 into z cap, if you have like this, then a1 comma a2 comma a3, they are the components. That component will change if you change the coordinate system. Okay, so this is Cartesian. If you change it to the say spherical polar coordinate system, I cannot write like this: a1 into r cap plus a2 into theta cap plus a3 into phi cap. Can I write like this? Means no, you cannot write, because a1 is no longer a1, it's a new value. a2 is similarly new value. So a vector is a quantity which will transform like the coordinate transformation. This is the definition of a vector. So a1 cannot be there. Instead of a1, you say b1, then it is okay. Now this is, I will put a tick. So b1 into r cap, b2 into theta, and b3 into phi, then it is okay. Where b1, b2, b3 are related to a1, a2, a3. That is fine. So therefore, so there is a what? So because of that, what is the trouble? The trouble is these numbers a1, a2, a3 depend on a particular coordinate system. Coordinate system is what is known as frame of reference. Both are same. In physics, we say frame of reference. In mathematics, we say coordinate. So therefore, when two people are there in two coordinate systems, one person is stationary, another person is moving, we say that one person is Cartesian, another person is something like spherical. It is equivalent. In mathematically speaking, Cartesian to the spherical polar coordinate system transformation is similar to stationary frame of reference to moving frame of reference. Okay, how a mathematician is going to view, how a physicist is going to view. So they are similar, and because of this reason, what happens is the vector will undergo transformation. Transformation means a1 will change to something new, a2 will change to something new. This kind of transformation is there for vector, and for tensor, of course, naturally it is the same thing, because tensors are extension of the vector only, and therefore the components of the tensor will also undergo the coordinate transformation rule. Coordinate transformation will dictate how the transformation will take place for a tensor. So all these troubles come for vectors and tensors. But now, why do you want to discuss so much is, now we have a scalar. M into C is a scalar. So this particular scalar will not undergo any kind of transformation. So a scalar will remain as the same scalar in all the coordinate systems. And therefore, this is known as Lorentz invariant. Now we say that this quantity doesn't undergo any change, and therefore people in different frames of reference, all the people will make the conclusion that x mu is always equal to mc whole square. So this is a conclusion that you have, and therefore this quantity is known as the Lorentz transformation, not transformation, Lorentz invariance. So now that this idea is clear, okay, so you know what to do. So you start with some equation, and then do some kind of what do you want to find? You have to find out one vector, and you have to find out something with the velocity of light, and then do a little algebra, and then you will be able to get some kind of product like this. That's all about it. So this is what you have to do in the case of the electrodynamics. So let us now see what can be done for the continuity equation. So in the case of the electrodynamics, you have the continuity equation, namely the divergence of J plus dou rho by dou T equal to 0. Now the question is this: how to rewrite this equation in the in some kind of covariant, contravariant, or if derivatives are appearing, respective derivatives. So what can you do? So the answer is clear. One thing is clear here, that directly one 3D vector is visible. So one three-dimensional vector is quite readily visible. That's fine. And we need another component with respect to the time and the speed of light, but that is not directly there, and therefore we can make a small adjustment. What kind of adjustment you can do is, we'll write like this. You don't have any speed of light entering into picture. Therefore, if I multiply by the speed of light like this, okay, rho is the charge density. So since the speed of light is not there in the original equation, we can multiply, but however nothing will happen because of time derivative. Now in order to make the compensation, I'll put a 1 by c. Now this equation is same as dou rho by dou t. So first term is over, and plus the remaining terms are as usual. Of course, whether you want to expand and write, that's fine. So it is dou x jx by dou x plus. So expansion is optional, but I'm just writing down in the expanded version, that is equal to 0. So on the right hand side is 0 is there. So now you have this equation as the continuity equation. So then what happens is, if it is the case, then we have to identify what could be the 4 vector corresponding to this situation. As you see that the 4 vector corresponding to this situation will be 0. Okay, only when the 0 is there, I can get a 1 by c into dou by dou t. Now you have to remember one thing, you will get a doubt whether to write 1 by c into 0 as a first element, or should I write a 0? That should be clear. Then only they can write the first element. Second element, third element, there is no confusion. You can simply write down jx, jy, jz. That is not a problem. So how do I know whether I have to write 0 or 1 by c into this expression? And that will be known if you remember what is the divergence. So do you remember what is the divergence we have done? Here it is. See, this is the portion that you have to remember. So now you see this one. So if you remember this expression for this, now you see that 1 by c dou by dou t has to come. Okay, 1 by c dou by dou t should be the operator. That operator is operating on whatever element that you have. This can be this is operating on something. So therefore, 1 by c dou by dou t should be there, and then whatever left out in this box or in this circle, for example, that is the component. So what is left out in this circle, that's what you have to see. So if you remember that, and coming to this, now you see that 1 by c into dou by dou t is there. It is operating on 0. Therefore, 0 is correct. Okay. So keeping that kind of information, let us now write down. Therefore, x mu will be equal to, so 0th component means the one with reference to the time. That means the one with reference to the speed of light. These things will come in the 0th component. First 3 elements after that will be the standard 3-dimensional vector, namely the current density jx, jy, jz. And that's all. So that will be the x mu, and suitably you can also define with a -1. Of course, yeah, that is first element. There is no need to change any sign. So 0. The last 3 space component will be minus jx, minus jy, minus jz. So comma. This is how you define. And of course, and you also have the definition. This definition is there already. Definition for the derivative, which is dou divided by dou x mu. So if you are going to make use of these definitions, I will be able to rewrite this equation in a compact notation. Okay, so now we can write down the compact notation in one line. So how do you write this compact notation? Dou mu. So now we'll say that dou mu will take care of 4 components. Remember, 4 components it will take care, because whenever you write this index in the Greek symbol, we should tell over what range it runs. It runs from 0, 1 to 3, and then full stop. So totally 4 components are there. So dou mu means it takes care of 4 components. Where are the 4 components? So this will be the first component, that will be the second component, etc. Therefore, dou mu is okay. Operating on what? So this is the dou mu. Dou mu is operating on the vector x mu. So instead of saying x mu is a very generic one. Without referencing to any particular variable, x can be any generic one. But now that we are talking about the current density, we can say J mu. It doesn't matter whether you really write J mu or x mu. It is actually doesn't matter. But it is better to write J mu because we are talking about the current density and then the continuity equation. For that purpose, we can write down it as a current J mu. So I'll write down that this particular J mu will be equal to 0. So now you see that the continuity equation in electrodynamics looks in a much compact way. Not only that, not only compact. In addition, the right hand side is 0. 0 being a scalar, this is invariant. So I'll write down that this is Lorentz invariant. So this is the conclusion. So which means that this particular equation. So where is that equation? Delete. Here it is. This one. So this continuity equation. Okay. As you see that it has a space part and it has a time part. So the space and the time has to be merged together into a single element known as space time. And these J mu or dou mu, J mu, etc. So these are known as. So this is known as the forecurrent. If you don't like the forecurrent, we can say that this is known as the 4-vector current. Okay, whatever it is, this is fine. So J mu is known as the 4-vector form of the current, or simply you can say forecurrent. And the respective derivatives are 4-dimensional, and therefore this is Lorentz invariant. It also tells you there is something important here. So what is the invariant? Because of the Lorentz invariant, what is interesting is that since the this particular equation, namely the continuity equation, is talking about the conservation of charges. Okay, because of that reason, what happens is invariant means if a particular physical system is charge conserved in one frame of reference, then in another frame of reference also charge is conserved. So that means charge conservation is guaranteed in all frames of reference. That is the conclusion that we can get it because of the 0, that is, I mean, the scalar 0 coming into the right hand side. Otherwise, general doubt may be there. Okay, you are having a stationary frame of reference where the charges are conserved. But if I am going to have a moving frame of reference, whether the charge is conserved or not, how do I know? If I ask this question, we don't have a way of writing down mathematical proof. But this equation clearly tells that in every frame of reference, the charge will be conserved. So that is the important conclusion that we are getting. So once this is clear, you are now in a position to write down other equations of electrodynamics. Okay, so maybe I will take another equation. So maybe the potential equation I can take, or let me therefore start with the. I think the important equation is the Lorentz gauge. So maybe that I will discuss. Lorentz gauge condition is very important condition in electrodynamics. What is that condition? You already know. Okay, 1 by c square into dou phi by dou t plus the divergence of the magnetic potential is equal to 0. So this is the equation, what is known as the Lorentz gauge condition. And for your reference, we will write down what is Coulomb gauge condition. The Coulomb gauge condition is divergence of A is 0. Now, once you have the idea of the 4 vectors and the relativity, something is straight away visible. What is visible is this equation has no what you call no time component, isn't it? So that is something trivially visible there. But here you see that this is of course space component ax, ay, az. This one is there is something c is coming and there is a t is also there. So certainly this is the one corresponding to the time component, and therefore it is possible to define a 4 vector. Remember, 4 vector means 4 components should be there. 0th component will be time, the remaining 3 component will be space. So my 0th component will be this, the remaining 3 components will be this. So here, when you don't have the time component, the question is that where is the time component? So 4 vector definition itself is not possible for this Coulomb gauge. So when you don't have the 4 vector itself, you don't have any concept of Lorentz invariance. So straight away we can make a conclusion that Coulomb gauge is not Lorentz invariance. That means is not Lorentz invariant. Means if you perform a Lorentz transformation, now what is the meaning of Lorentz transformation? Means simply, physically speaking, I am moving from one frame of reference to another frame of reference. That's all. If I am shifting my frame of reference, mathematically we say that we are performing the Lorentz transformation. And when we do that, Coulomb gauge condition will be affected. Not invariant means what? Coulomb gauge condition will be affected. That means one person's divergence of A equal to 0 will not be divergence of A equal to 0 for another person. That means in a simple language, I'll say that in the moving frame of reference, del prime dot A prime is the moving frame of reference, may not be 0. So that means your gauge condition itself will be destroyed when you are making a frame to frame changes. So that is the one important conclusion that can be done about this. But interestingly, what happens is for the Lorentz gauge condition, it is not so. So therefore, let us see what will happen to this case. For this case, you can now rewrite. How do you rewrite this? Is I want 1 by c. Remember one thing, we already have the definition, and based on that definition only, we are now making some kind of manipulation. The manipulation requires 1 by c into dou by dou t. That is the operator that you have. This is the operator. I don't have 1 by c square in my operator. Therefore, 1 by c only should be there for operator. Dou by dou t should be there only for the operator. Then whatever is there, you have to make some kind of rearrangement. So what rearrangement will you do now is that once this is clear, there is a phi here. So that phi can be written down. But however, I have not written here 1c here. Therefore, that has to come here. So this is how this equation can be written down. Plus the rest of the equation can be written down like this. Do it plus xl. 2 more terms here, then equal to 0. So this is clear. Now, of course, in one of the notes that we have seen, or we have proved that it is very easy to prove. Of course, I have sent you the notes showing the proof. What is the proof is that phi by c physical dimension. The physical dimensions of the phi by c will be the same thing which is corresponding to the ax, or we say that A vector. So this will match actually. Interestingly, it will matches, and therefore you can easily show this. Okay. Right now it is not important for this calculation. Now once this is clear, so then what happens is, so we can define like this. So what will be your x mu? X mu will be 1 by c dou by dou t. If you leave it, we have only the phi by c, comma, then the space components ax, ay, and az. And similarly, the x mu can be written down with the positive of the first component and negative of the remaining components. All of them are negative. Like this you can do. So once we have this definition, and not only that, you also have the definition for the dou mu, that is equal to dou by dou x mu. So with all these definitions, what you have to do? You have to do something for this. So how will you write this equation? So we can write down this equation as the dou mu of, so I'll say that this is dou mu of x mu. And remember that this x mu, of course, x, as I already told you, x is okay. Anything you can define it as x. But since physically speaking, all of them will have the same dimensions of the capital A. Capital A is what? Magnetic vector potential, right? So therefore, since we are talking about magnetic vector potential, it is better to say A mu instead of X mu. Okay, therefore I will now say that this is A mu. And the right hand side of the equation is 0, isn't it? That's important. This expression is 0 is there. And our conclusion is that this being a scalar. So ultimately, since right hand side is becoming a scalar here, why that sound came, I don't know. Okay. So now the conclusion is that Lorentz gauge is invariant. So that means a person working in the Lorentz gauge, he then what happens is when this is made sure, then even after the Lorentz transformation, that means shifting from one frame of reference to another reference frame, the gauge condition is intact. That means original gauge is maintained, and therefore what happens? So what is the advantage of this is, as long as you guarantee that the Lorentz gauge is satisfied, what is the advantage is that the potentials will satisfy the wave equation. This is very important. Otherwise, if the potential is not going to satisfy the wave equation, we don't have the solution to the wave. We don't have the solution to the electromagnetic potential. That means it will be unknown. Okay. So when it will be known to you is when the differential equation is solvable, the quantity is known to you. If a differential equation is, you don't know how to solve a differential equation, then we don't have the solution also. So therefore, remember that A mu, from where will you get the A mu is solution to the wave equation. Where from you got the wave equation is because of the Lorentz gauge condition. If the Lorentz gauge condition itself is violated, that means it is no longer valid, then A mu itself cannot be determined. And that is where the story
Hello, sir. You are not audible.
now I restart. Yes. Now it is coming. Okay. I think now this is coming. Okay. So what was the conclusion that I was talking about is that which gauge condition is very important. That's what I was talking. Okay, Lorentz gauge condition is going to retain the relativistic transformation in a natural way, and therefore Coulomb gauge condition is not going to be useful, because if divergence of A is not equal to 0, then the A means magnetic vector potential, that itself cannot be calculated using the wave equation. That's what I was telling. Wave equation will come only when you have the gauge condition satisfied. If the gauge condition itself is not there, you don't have the wave equation. If you don't have the wave equation, you have a differential equation whose solution is not known, and therefore we do not know how to calculate the this A. A means magnetic vector potential. So therefore, keeping the Lorentz gauge condition is saving you, in the sense that irrespective of whatever frame of reference you are, the gauge condition is guaranteed to be satisfied, and therefore we can calculate the magnetic vector potential using the same wave equation. Therefore, this condition is important. And similarly, of course, you can write down one more. We can take some other equation and write down. So which equation would be better to write last? We can write down one more equation probably. Maybe the wave equation itself we can take. Okay. So that could be the more interesting one. Probably because we were discussing about wave equation. Let us see how to write the. It's the same wave equation that you studied in optics or acoustics and optics or whatever it is, waves and oscillation in your undergraduate. The same wave equation is only getting coming for the electromagnetism also. And what was the equation that you had? If you remember that, we have to write down two wave equation, one for the electromagnetic potential corresponding to E field and one more for the B field. Okay, so but both of them will look same. I'll write down that, then you can easily understand. So phi means, electric potential, not static. Okay, it is not static, but we say electric potential minus of the del square of the phi is equal to rho by epsilon 0. And you also have the corresponding equation for the magnetic vector potential. Mu naught into J. Okay. So here, what is that? This is the wave operator you already know, right? The wave operator is this 1 by c square dou square by dou t square minus the del square, and that's all. So this is the operator that you have. On this operator, either phi can be acting here or capital A will be acting. So this is the wave operator. And interestingly, we are going to rename the operator now. So the operator that we are going to call is a box operator. I'll now say that this is box operator. And we are going to give a name for this. This is known as the D'Alembert operator, but I think D is written in small letter. It is only for the sake of compactness we are defining. Otherwise, mathematics is same thing. This big thing we don't want to write every time. So that's why we are defining it as a box operator. And in fact, you can understand why it is so. People have given the name like this. Already you have the name for this del square operator, right? It's already there. It's known as the Laplacian. So the question is that when you are having a name Laplacian for the three-dimensional Euclidean space, you can ask the question, what will be the corresponding Laplacian for four-dimensional? That is how the question comes. Laplacian means three-dimensional. For four-dimensional, what is the name? So the answer is, okay, you can simply call by the name four-dimensional Laplacian. That name is okay, fine. Four-dimensional Laplacian. Now this four-dimensional Laplacian is what we are going to give the name D'Alembert operator. So D'Alembert operator is nothing but equivalent to 3D Laplacian, or we say that it is nothing but it is 4D version of the Laplacian operator. The only thing is that this is not Euclidean space, and therefore time component enters into picture. 4 components should be there, right? Already 3 components are there. 1 component comes like this. So therefore, this is the idea, and therefore based on this idea, you can write this equation in this particular form. Like I can put a box here. This is a box, the first operator I'm talking about, and then operating on the phi. So this is operating on the phi will be equal to rho by epsilon naught. And similarly, the second operator will be box operating on the capital A vector will be equal to mu naught into J. So there is a little bit of compact way of writing the equation. So that is the only advantage. But other than that, okay, the purpose of the notation is not that. This is one thing. Second thing is, this particular operator has a built-in structure. As you can see that del square takes care of 3 space elements. The first element, 1 by c square into dou square by dou t square, takes care of the time component. That means the D'Alembert operator is interestingly somehow already taking care of the Lorentz transformation, or whatever it is, that the so-called special relativity. The property of the special relativity is already built in this kind of an operator. Whereas if you forget about the time component and see only the Laplacian operator alone is not invariant under Lorentz transformation, because Laplacian operator doesn't have Laplacian operator doesn't have the time component. Therefore, 4 vector cannot be written down. Therefore, there is nothing like Lorentz invariance for that. So the story is same thing like this. So the story is the same as 3-dimensional delta. So when you have only 3-dimensional, automatically there is no question of Lorentz invariance. So same thing happens here. Whenever a quantity is having only del square, then such quantities are not Lorentz invariant. Which means you have to remember, which means what? Which means that if you want to write down the electrostatic potential. Okay, remember static. Okay, we are going back to the static. Do you remember what is the electrostatic potential? It is del square phi is equal to something like minus rho by epsilon naught. Right? This is how you have the equation for the electrostatic potential. Now remember that this potential is not electrostatic. This is electromagnetic potential. So this electrostatic potential, this is not Lorentz invariant. Why it is not Lorentz invariant? Because only del square is there. Where is time component? Time component, speed of light, nothing is there in this equation. And therefore, this quantity doesn't fit for discussing the Lorentz invariance, and therefore, naturally, it is not Lorentz invariance. So people in different frames of reference will find their own values for the electrostatic potential. Their one value cannot be compared with the other person's value. So that is a trouble here. But if you consider this formulation, this square, that is what you call the box operator, is already invariant under Lorentz transformation, and therefore these quantities will remain as such as we change the coordinates from one frame to other frame. And that is one thing. But before that, I would like to tell you that we don't have a C square version for our derivative. Remember, you have to be careful when I am discussing about the time derivative. We don't have C square. We also don't have second derivative for time. You see this? Till now, whatever we discussed, remember what is the time derivative? This. So this is the derivative operator. We don't have square here. We also don't have second derivative. These are a first derivative. So 1 by c dou by dou t is we have, but we don't have 1 by c square dou square by dou t square. But as you can easily see that this looks like, squaring it. It looks like that, right? And therefore, because of this reason, now we can quickly write down. One thing you can quickly write down, that dou mu. So what is this? So that will be equal to box. So this is what is the important. Quickly you can decide the meaning of this. In fact, you can easily understand how this comes is, there is only one line. If you write that one line, it will be clear. I'll write that now. So first dou mu, what is the component for that? 1 by c dou by dou t. Okay, that is the component. Then after that comma, then you have a minus. Minus of what? The other x, the space components. Okay, whatever be the case that you have here. So after that you have a minus here, you have a minus here, you have a minus here, and the corresponding plus values are there here. So one set of plus values and one set of minus values are there, but all of them are space derivatives. So let me put space derivatives now. Space derivative, comma space derivative, comma space derivative. That multiplied by this dou mu is where. Now you put it this dou mu. This dou mu is 1 by c dou by dou t. Now you have a minus dou by dou x, minus dou by dou y. That's all. That is the meaning. And of course the commas are there, therefore the unit vectors, you know how to multiply component by component. First, that is 0th component multiplied by 0th component. How much will you get? 1 by c dou square by dou t square. Now only interesting point comes. 1 plus 1 minus is there. That's why minus will come here. Dou square by dou y square minus dou square by dou z square. So therefore, you can easily see this is x, this is y, minus dou square by dou z square. So as you can see that we are able to generate the three minus signs also, and the second order derivatives are also coming into picture, and that is nothing but the wave operator. Now let us go back here. So this del square operator has the dou square by dou x square, etc. And this all came into picture. Therefore, you can ask the question, what is box operator actually? Box operator is nothing but dou mu dou mu. So this is what you understand. So therefore, because of this reason, what happens is you can actually write down or you can combine them. So that is the advantage now. Because of this kind of relation dou mu, these two equations will be combined to a single equation. Now that is something interesting. Okay, maybe it requires one or two steps. Okay, then only you'll be able to see. Now we can ask the question: these are two equations, right? How can you combine into single? The interesting thing goes because of the four elements in this dou mu component. So maybe I will show that that additional step here. So I don't have space. Little space is here. Shall I will delete something here and then write down. Okay. Okay, this portion I'll delete. Okay, so what was the first equation? The first equation was box. Box operating on the phi will be equal to rho by epsilon naught. We are going to rewrite a little bit. If you rewrite this interestingly, you'll get the answer. So what is box operator? Box operator is dou mu. That is fine. Then that operating on phi is equal to rho by epsilon naught. The same thing. That is also clear. Now comes the question that you have to now identify the space component and time component, or we say zeroth component and the remaining. Here only you have to think, or you have to make some adjustment. Let me write down second equation also, then it will be clear. The second equation is box operating on A equal to mu naught J. Okay, I'm writing same thing. Maybe I'll show that. Is that right? This one. These two equations only I'm writing and then trying to make some manipulation and remembering that the box is nothing but dou mu. So same. This is what I'm writing right now. So the box operator is exactly rewritten as dou mu. That's all. This phi is this phi only. Similarly, when you write this expression, this looks like is dou mu operating on A vector is equal to mu naught into J vector. Now is the interesting point is that you have an equation number 1 here, you have equation number 2 here. We are going to merge these two. Combining means we are going to merge both of them and write it as a single equation. How we can do is, this is three components are there. Three components of space part. I will say that spatial. Spatial means the space part. So if the equation 2 contains the space part, then I believe that, we don't know, but that's what I have to think. We think that equation 1 should contain time component. Does it contain time component in the first part? So that is what you are going to think. Okay. Why do you want to think is that there is no doubt, because A vector is there, right? You don't have any option for time there. So A vector is actually three-dimensional space vector. So that you make sure. Now here something is not clear because this is actually a scalar quantity. Okay. So whether time component is there or not, it is not clear. But now therefore what you do is, you ask the question, why don't you rewrite this equation in a slightly different way? So therefore what you do is, let us try to rewrite, or let us try to manipulate this. How do you manipulate is that I write down like the same dou mu. Same thing I will write like this, but time component means something like 1 by c, or c speed of light should come, right? Therefore, apparently, I need a 5 by C, for example, because you should remember why 5 by C is coming. Sometime back only I told you that 5 by C will have the same dimension as the magnetic vector potential. So these, the previous knowledge that you have, you try to use and then manipulate. So I'm going to write 5 by C here. If I write 5 by C, then the right side also you have to put a 1 by C. So let me put a 1 by C on the right hand side. So 1 by C rho by epsilon naught. That's all about it. So the same equation is now rewritten like this. Now I am happy to see 5 by C there, because the same 5 by C was used sometime back in writing the 4 vector. Maybe I think I did not delete. Here it is there. 5 by C is there. So when you have a 5 by C, together with the 3 components of the capital A vector, you are very happy to say that that is called the 4 potential. Actually, I didn't write the name. If you want, you can write down the name better. This is the electromagnetic potential, right? So I can call it by the name 4 potential. So I am able to now see 4 potential in these 2 equations. That is first point. And second point is, when you are talking about the current density, let us go back. Here, this is known as the 4 current. Okay. So do you remember? Maybe we have written somewhere, but let me write down here. This is known as the 4 current. Now this 4 current has C into rho will be the first element. Therefore, I need C into rho whenever we are talking about 4 current or 4 vector, in general 4 vector. So what are the things that you are looking for? C into rho. Remember, C into rho is one thing that we are looking for. And then phi divided by C is the another quantity we are looking for. So where are you looking for these quantities is that we are looking in this equation, the current equation. Yeah, in this equation number 1, now this is the equation that we are discussing. In this equation, do you have the required things? So 5 by C is there, so I am happy. I'll write down once again. Dou mu. 5 by C is there, so I think there is nothing to worry about that. But I don't have C rho here. But remember, C rho I want. I don't have C rho. I have rho by C. So what I want is, so I will once again rewrite C into rho only I want. Therefore, I want this and divided by, already C is there. I am putting additional C in the numerator. Therefore, that must be a C square. Then this is an epsilon 0. So let it be epsilon 0. And therefore, this will be your first equation. And interestingly, okay, somebody is joining. It's okay. And there is one more thing. And what is that one more thing is, do you remember what is C square? I think I will write here. So what is 1 by C square? 1 by C square is nothing but mu 0 epsilon 0. Do you remember this? So this is the one that we will be using now. So substitute now that expression. So if I substitute mu 0 epsilon 0 here, the right hand side becomes 0. 0 is there, that's fine. And mu 0 epsilon 0, I have to multiply. You tell me what will be cancelling. C square will go, mu 0 will come. Is it correct? So mu 0 epsilon 0 if I put, 1 will be getting cancelled and then I am getting this. And that's all. So that is equal to dou mu. Operating on 5 by C. And that's all. This is the interesting equation that you have. This is the equation number 1 now. So equation number 1, we already started here, right? This equation, same equation number 1 got transformed to this. Equation number 2 is there here. No need to change this. And now what happens is these two things can be combined. In what way you can combine is, in the left hand side you see that 5 by C is there here. 5 by C is there. The remaining 3 components are there here. I will say that AX, AY, AZ. So I can now combine and say that this is A mu. Come to the right hand side. In the right hand side, 0th component is there here. So I'll write down 0th component, 0. And then the remaining space components are there here. I will say that JX, JY, JZ. So that will be known as J mu. So as you can see that 4 potential and 4 current are coming into picture from the first equation and second equation. And because of this equation, we have the final equation. What is the final equation? Is the box operator. What is the box operator? Do mu, do mu. So whenever I want, I will keep do mu, do mu. Whenever I want a box, I can keep box. Both of them are same. Okay. So because we are going to the final form of the equation, I don't want do mu, do mu. So do mu is only box. So that is over. Then pi by c together with this a, all of them is known as a mu. So I'll write like this. That is equal to, that's over, equal to, come to this side. If I come to this side, you have 0, j. 0, j is j mu. So therefore, I have a constant mu naught into j mu. And that's all. And this is really surprising. What is surprising is that the two equations have got now merged into single equation. Now, what are those two equations which got merged? So if you see here, these are the two equations which got merged. And these two equations are nothing but the wave equations that we have here. This one, it is the same thing as the wave equation. And from where you got this wave equation? You got this wave equation from your Maxwell's equation. And therefore, ultimately, this is the ultimate story. The ultimate story is that the set of all Maxwell's equations has been rewritten. Finally, the set of all Maxwell equation has been rewritten in a much more compact way. That is the compact way that you have here. Here it is there. This particular single equation saying that the box operating on the A is equal to some constant times the 4 current. So this quantity is nothing but it is the set of 4 Maxwell's equations written in potential form. Okay, so therefore this is what we say the covariant way of writing down the electromagnetic equations. So it contains all information. So what are the information that we have done today is that the continuity equation and then the Maxwell's equation. And that's all. Only continuity equation together with the Maxwell's equation provides the entire electromagnetic theory. If you want to talk about the material medium, okay, auxiliary equation can be taken. Auxiliary equation means B equal to mu into H, okay, in material medium. That is an auxiliary equation coming the information about the relative permeability and electric permittivity. That information is coming from the auxiliary equation. But other than that, the continuity equation together with the 4 Maxwell equation provide complete electromagnetic theory. And that complete electromagnetic theory is now compactly written down in a single equation. So now you see Maxwell equation is not 4 equations. Now it is compressed into a single equation in the potential formulation. And remember that this equation is valid under the Lorentz gauge. And the Lorentz gauge itself is invariant, and therefore we can now happily say that this kind of equation is invariant under the Lorentz transformation. So this is the important conclusion that we can get. So this is exactly what I have written in the form of notes. Like I have written maximum detail in the notes so that it is easy to read. When compared to the textbook, I have written additional details. So you please go through that. So I think this is the last thing that I have written in that particular notes. If you have any more questions on like electromagnetic wave propagation in lossless medium, lossy dielectric, perfect conductor, I have already sent notes for that also. You read that, and then if you have more questions, we will be having another Google meeting, and then you can ask some questions.